specified properties. They often come with machine-checked proofs, and many of them are sort of have high degrees of automation here. So things in the space are like the Koch theorem proving language, F-star, Lean, Liquid Haskell, which you saw last week, Idris, and there's others as well. So I think that we've sort of built the tools that we think people will use in the future, but there's still sort of a gulf between the tools that we use now and these tools that the PL world has sort of put out there that have these nice, even stronger properties. And what I'm interested in is, how do we build the bridge that gets us from here to there? Right, so the kind of research question that I'm looking at is, how do we build a bridge from scripting languages, where scripting languages, I really just mean sort of things that have highly dynamic behavior, maybe no type system, but might have properties like memory safety, up to these languages that let you do things like prove full functional correctness as part of the language. Okay. So I have a few design goals in mind sort of criteria that I'd like to satisfy as I think about this potential answers to this question, which is that I would like things to be gradual, meaning you could take a program that has sort of no verification stuff sprinkled into it and still be able to run it. And then you ought to be able to do a piecemeal kind of fortification of the program where you maybe add a few annotations or prove a few properties about certain functions in your program, but you don't have to do the whole thing at once, okay? So, because I just think that's sort of a losing proposition. If you have to take, 1 million lines of Java code and port it to Agda, let's say, then that's gonna just not work out very well. So I would like to be able to add in bits of verification and still be able to run the program. And that may mean that you sort of can prove things about parts of your program, but not about the overall behavior of the program. And you'd like to have the things that you proved and their interactions with the sort of untamed parts of your program be monitored in a principled way, so that you can still make nice claims about what happens when you run your programs without having a kind of all or nothing verification technology. And that process of doing that ought to be sort of reinforcing that if you take the time to start to write down some specifications and maybe prove some things about some of the components of your program, that more good things should start to happen, more properties can be proved, and so on. And it ought to be productive in the sense that there ought to be some good incentives for taking the time to do this kind of work. So maybe it makes your program run faster. Maybe you get immediate feedback on the programs that you're writing. So if you write down a spec, it would be nice to know, for example, if the program doesn't meet the specification, well, what's a good example of where it doesn't meet the specification, so that this isn't just sort of a cost that the programmer has to pay, but this is something that's actually helping them be productive and moving them further along with their goals. And to the extent possible, I would like this stuff to apply to a broad range of programming languages and idioms and things like that. So to the extent possible, I'd like these sort of techniques to be universal. Okay, so so I have kind of a solution that I'm going to talk about today, that says that you can obtain this by using this combination of techniques, which are having runtime enforcement mechanisms for the properties that you care about, and then using a combination of symbolic execution and abstract interpretation. Now, if you don't know what these things mean, that's fine. We're going to talk about them. But I sort of have a recipe that I think will deliver on this, this question and satisfy these design goals. And we'll see a couple of instances of it today. Okay. All right, so let's take a look at the details here. So I'm inspired by work on and the success of gradual typing, which is a big theme from the programming languages community over the past 10 years or so. And it's something that, you know, has sort of come out of our community. It's really been adopted by the big industrial players here, where they've developed their own gradually typed programming languages. And in some sense, gradual typing is kind of a miniature version of this vision that I have, you know, that I would like to see, where the idea is that you go from, say, scripting or untyped languages to typed languages, and you can start to gradually add on type annotations. You can have parts of your programs statically verified against the type specifications that you write down. When you run, you can run all of these programs, even if the whole thing isn't verified against the type. And there's a good story about how those, the abstractions that the types are giving you are actually enforced and checked when you run programs. And there's a bunch of, you know, examples of gradually typed languages that are being used today. The one that that I sort of work in the most is this language called typed racket. So so typed racket is kind of a sister language to this, its untyped counterpart called racket. And the idea is that you can write down code that looks just like racket code, but you can start to sprinkle in some type annotations here. So this module is actually written in the typed sublanguage, and this module is written in the untyped sublanguage, and they can interact with each other. Okay, so we can make calls to functions that are defined in the type module here. And the argmin function here, what it's doing is it's saying, okay, well, you give it, so it's parameterized over all types A, and it's saying, if you give me a function that sort of tells me the cost of that thing, and a non-empty list. So this is just saying that you've got a list, but there's at least one element in the list, a non-empty list of those things, then it'll give you back the element that has, or an element that has a minimal cost, okay? And here I've got two clients of that in the untyped module, and one of them actually has, you know, if we were to consider this as a typed module, it has a type error in it. Okay, so the first use here is fine. Sorry, it's just reading off what I showed. But when you run this second one, okay, this list of things here is a list of symbols, which are not, the important thing is they're not numbers, and our cost function is the identity function here. So what happens is that eventually we're trying to compare the elements of this list with less than, and it doesn't work, okay. Sorry, I see something's coming up in the chat. All right. Okay, so it sort of manifests as a runtime error, and what I'm sort of showing you here is that this part of the program, we can statically verify that it satisfies all of these specifications here, but you can use it in a way that violates them, but they get caught at runtime. Okay, so so it's giving us this nice gradual property of programs can be of sort of mixed components with different levels of verification in them, and the properties that you expect are going to be checked when we run them. Okay, and the kind of mechanism behind this in Racket is that after type checking has happened and we've, verified this code over here satisfies the types that you wrote down, then uh, then sorry, then what happens is we just erase the types and this becomes an untyped module and a thing called a contract, which looks a lot like the type that we wrote down, but is actually just a sort of piece of of a program, right? It's a runtime concept here. Gets attached to the boundary between these two modules, and that's going to regulate the flow of values from one module to the other. And every time that a value flows across one module and into the other, the parts of the specification that are relevant will be checked against it by, run. So this thing like real is just a predicate in bracket, and it'll be applied to the value. And if it is real, we let it go through. And if it isn't real, then we signal an error. And the errors come with some indication of which module here broke the agreement. Okay. All right. So let me talk now about sort of my view on program verification. So this thing in blue, consider this just sort of any program. And when you run the program, maybe you get a crash, okay? And what you would like to do is sort of rule out crashes. That's sort of one view of what program verification is about, is ruling out crashes. And type systems are, maybe one of the most widely used kind of verification technologies. They're kind of lightweight verification technology. And the kind of verification that's going on there is that if you've got a program that satisfies some syntactic restrictions, namely that it's well typed, then you have this property that when you go to run it, it doesn't go wrong. Where wrong here is some thing that's precisely defined, but what it means is that there are a certain kind of runtime error that can't happen. Now, there's usually other kinds of runtime crashes that can happen. So if we think about something like Java or Haskell or OCaml or typed languages like that, right? The kinds of errors that they rule out are you're never applying something that's not a function. In the case of Java, you're never invoking a method on an object which doesn't have that method defined, and things like that. But it's not ruling out things like divide by zero errors or things like that. So you precisely define a class of errors, and you prove some theorem saying that, well, if your program's well typed, then it can't possibly reach a certain state, which is this wrong state. And it's modular in the sense that you can take out subcomponents of your program and annotate them with their type specifications. And if you still have a well-typed sort of module, well, so long as you plug in the components that satisfy the specifications you wrote down, you still have this property that it can't go wrong. Okay. Right. So you can plug in, different programs that have this spec, and it won't crash. If we move on to thinking about gradual typing, okay, there's sort of an adaptation of this theorem, because things may go wrong at runtime because you have untyped components in your program, but we can kind of distinguish between the wrong states that are the fault of the typed part of the program and the wrong states that are that are the fault of the untyped parts here. And you can't prove the well-typed programs don't go wrong anymore, but what you can prove is that well-typed programs can't be blamed, right? If something goes wrong, it's not a blue wrong state. It has to be some other color here. Okay. So my view on kind of modular program verification is taking kind of abstracting away from the details there, is that you've got some notion of components, program components. You've got some notion of specifications that sit at the boundaries between these components. And you have some kind of mechanism for attributing fault or blame to the different components. Basically saying, when you've got a specification that's regulating the interactions between these two, it can tell you which party violated the agreement when you run it. Okay. And often that's going to be done with some kind of runtime mechanism that checks the properties that you wrote down here. Okay. And modular program verification just means that you can talk about a component in isolation along with the specs for the things that it's linked against. And you want to be able to say, okay, for all of the possible instantiations of this component, it can't go into a crashing state that is the fault of the program that I'm looking at and trying to verify. Okay. I mean, you have no hope of verifying the stuff you don't know about, but the program that you know about, you want to say that it's not, you can't reach a bad crashing state here. Okay. And you ought to be able to establish a theorem that looks like this, saying that whatever your verification technique is, it says verified programs can't be blamed. So right, gradual verification is enabled by runtime enforcement. Let me sort of show you an example of what I mean by that. So this is a program written in OCaml, so functional language, typed functional language, and I'm going to step you through sort of some of the computation that goes on here. But I want you to imagine that we're looking at maybe this blue program here, and it's interacting with something that we've linked against, and we've got some specification here. The specifications are going to be types that sit at the boundaries there. And I'm just going to show you sort of what I mean by who's at fault when we run this thing. And you might be thinking like, well, it's just kind of obvious who's at fault, right? Every time some value comes across, you just look at it and say, well, if it's not what it says it's supposed to be, then the person who, the party that's sending it, it's their fault. But this is complicated, okay, and not even something that you can decide when you're talking about a language with behavioral values or higher order values. So if we're allowed to only pass, say numbers and strings and things like that across these boundaries, then sure, it's pretty trivial. You just look at it and say, does it satisfy, I said you could only have strings up to length 10 or something, and this is longer. But if you've got objects or functions, things that have behavior, you can't just inspect it and decide some property about it. And that's the example that we see here. Okay, so I've got a blue program that's linked against, it's got some name F that it's being linked against some other component here. And then what it's going to do is it's going to call F, giving it a function. In this case, it's the 5/x function. So it takes some argument and does 5/x and then squares that, okay, multiplies by itself. All right, and what's the particular F that we're looking at here? Well, it's going to be the thing that takes in some function g, and then it just immediately crashes, okay? It just has some error and it divides by 0. Okay, so if we step through this, sort of the first thing that happens, right, is we're going to call F. Calling F means we're sort of jumping into the yellow code here. So you jump into the yellow code where now you're saying G is equal to that blue function that I passed in. I've got a type specification here for it. And then what this code does is it divides by 0. And it crashes, and since we're in the yellow module, right, this seems like this is something that is the yellow module's fault. And indeed, because all it does is take an input and crash, that's it really is the yellow program's fault here. But let's maybe change it up a little bit. So instead of just crashing, let's have the yellow program make a call to the function that it was given. Okay, and now we're going to see a sort of back and forth between the blue and yellow code. So we do the same thing. We call into the yellow code, and now the code here is going to say apply G to 0. And what that's going to do is sort of jump us back into the blue code where X is now this value 0. And notice that we've gotten to this level where the specification here is just at the sort of base level of our language. It's not a function. It's not something behavioral. It's just, the yellow code, it had agreed to deliver integers. And we can look at this thing and say, well, 0 is an integer. So if yellow delivers something that you can look at and that satisfies the spec, then it is as if the blue code wrote it, right? In other words, the yellow code has satisfied its obligations here and delivered a value to the blue code that is what the blue code assumed was going to be coming in, and now it's up to the blue code to do with it what it will. All right, so now the blue code just divides 5 by x. X happens to be 0 here, and it crashes, and so it's the blue program's is blamed for this. Okay. All right, and now you might look at this and think, well, but the spec here is just talking about types, and the types, maybe aren't supposed to rule out divide by 0 errors. But I guess all I'm saying is that, if you were to interpret this as sort of ruling out all possible errors here, well, then this spec is just not tight enough, okay? So you could think about doing a refinement, okay? So this is like a liquid Haskell style refinement here, saying that, this interaction between the blue and yellow code is going to be monitored by this more precise specification, saying that G, is going to be a function that expects non-zero inputs. Okay, and if we were to step through this, or you could write the same thing down as a contract. So this is a contract that's very much like that refinement type. And what happens is, we make this call in. We have, we're going to transfer control back into the blue. We've got this refined specification here. And we get to this point, okay, where again, we're at a base value, 0, but we have a specification here that says, well, it's got to be something that's an integer, but it also has to be something that satisfies this predicate here, meaning that it's not equal to 0. But of course, it is 0. And so the yellow code is delivering something that doesn't live up to the spec here. So it's the yellow program's fault, and the execution would stop there and say, it didn't live up to its obligations. Okay. Now, if you look at this code with sort of what I've told you about how programs operate and this particular specification that we have here, you ought to be able to convince yourself that there is no function that you can put in here. You can't solve for the unknown here in any way that will satisfy this spec and cause a blue crash. Okay, so this is sort of what I mean by, we would like to be able to, if you were going to verify the this blue program, that's what it would mean, that there's nothing, you could put in something here that could crash, certainly, but only something that could crash blaming, itself, right, or somebody else, but not the blue program here. Okay. So that's kind of the runtime enforcement mechanism that I'm concerned with right now, are these contract-like specifications that sit at the boundaries between programs. And now I'm going to talk about kind of the mechanism, all right? And I've also said what it means to be verified in this setting. And now I'm going to talk about sort of the mechanism for how this works. Let me stop here and just say, I noticed that there are some things coming up in the chat, but it's really difficult for me to check the chat. So if anyone has questions at this point, you know, you can just interrupt me. And if there's stuff going on in the chat that you want to bring up, just unmute and go ahead and ask.
Hi, yeah, this is Edward, and I was the one who was asking a question in the chat. I was just getting really confused by this OCaml syntax, and I couldn't figure out which function was calling which function, because I thought F was calling G, but then you zoomed in and it looked like G was calling F.
Yes, so there's let me just sort of explain this, because it definitely can be confusing if you haven't sort of aren't familiar with this stuff. So here we're saying, we're just giving the name F to this yellow function, okay? The yellow function is a function of one argument, which we're going to call G, which is itself a function, and it's going to be applied to 0, okay? Then so after we name this thing F, then what we're doing is we're calling F with an argument. The argument is a function. That's a function of one argument called X, which is going to be an integer here. And it just divides whatever its argument is by, it does 5 over X, okay? So if we think about sort of what happens when you run this, right, you're going to run this expression, which means calling F with this argument, which means that you're going to jump into the body of this function with G meaning this function here. So that's why, you know, the slide takes a step to let G be this function in G over 0, okay? Right, so let G be this function here in G over 0. Now what happens is we're going to call this thing named G with the argument 0. So that's going to jump into the body of the blue function here with X being bound to the argument value. So this will, jump into 5 over X, where we say let X be 0. And so that's how we get to this point. Okay?
Okay, so none of these functions have names. And when you say fun G, you're saying G is an argument to the function. G is not the name of the function.
That's right. I mean, I'm using the let binding to name these functions, but sort of on their own, the functions, that's right, they don't have names. They're just values that flow around. So this is a function that expects one argument G and applies it to 0. This is a function that expects one argument X and does 5 over X. Okay.
Okay, thanks.
Sorry, may I ask one question?
Sure.
So I'm wondering whether this game of say, suppose that you have some mutually recursive functions that call each other, and assigning the blame may look like a game where you always pass the buck to the next invocation, right? So is it possible that the mechanism of eventually terminating and finding the culprit happens all the times, or one can build an example where this doesn't work?
Well, so the sort of contract mechanism here is really enforcing at runtime kind of partial correctness results. So I mean, it could be that things go on forever, and that, if something, I guess the way to say that this is that if you ever get to a point where there's some base level value that you witness going across a boundary and it doesn't satisfy the spec, then things stop. But you can always, as long as as long as it's sort of functional or object values that flow across, you kind of defer checking the properties until those things are interacted with. So you don't catch an error until you get down to kind of the base level here. I'm not sure if that answers your question, but
yes, thanks. Thank you.
Mhm. Okay, so like I said, I want to, I've said what it means to verify a program against a contract here, but now I want to talk about how you can do it. And the particular approach that we've been looking at is based on symbolic execution, which is sort of usually not a verification approach, but more of a bug finding approach. But I think you'll see how this works out for us. So the idea is that I'm going to take the program I'm trying to verify, and I'm going to link it against not a particular program, but a kind of symbolic program that is going to represent all possible programs that you could have linked this blue program with. And it's so these dark gray components here, their only purpose in life is to interact with the blue program in such a way that it discovers blue crashes, okay? So they're going to be these kind of like undetermined program components that have the property that if it's possible to reach a crashing blue state, then they will interact with the program in such a way that it finds it, okay? With the point that if you link it against these components and you run the program and it doesn't reach a crashing state, then you know that it can't, no matter what you linked against, it couldn't possibly cause a crash in the blue program. Okay, so the symbolic execution, one thing that's nice about it is you can just think about sort of how programs execute normally and see what's going on here, okay? So let's take this same example, and I'm going to link it against this dark gray code, which you can think of as like, I don't know exactly what it is yet, but I'm going to consider all possible things that could happen here. Okay, so I've got this, the weakened spec, so we ought to see that there are potential crashes here, potential blue crashes here. So so what happens? Well, the same thing, I'm calling f. Now f is some unknown function. So what happens is my argument here, this function of one argument x, goes off into some code that I don't know what it does. But there's sort of only, in a language like OCaml, there's only one way to interact with the function, which is you can apply it to something, okay? So this goes into some unknown code, but without loss of generality, the only thing it can do as far as causing a crash in the blue code is call the function on some argument. And it calls it on some, so we don't know which argument it is, but we'll just say, oh, we'll call G with some indeterminate argument here. And therefore, transfer control back into the blue code here and say, all right, let X be some unknown integer, right? Because it's got to be, if you're going to blame the blue code, it's got to deliver some particular integer such that 5 over X crashes. Well, when you get to this point, it's sort of clear, right? Now it's solved for X such that X is an integer and 5 over X crashes. And it's easy to think of one, it's just 0. And if you want to have a more automated way of doing this, you can encode these constraints as a formula that an SMT solver can solve for you. So in the same way that Ranjit was using SMT solvers for doing refinement type checking, here I'm using an SMT solver to figure out if there is a possible value for this unknown thing. But I'm only doing that at the level of base types in my language. So can you think of an X such that 5 over x crashes. And of course you can, okay? And one thing that's nice here is that, okay, so we've reached a crash. Sorry, let me step back to here. We've reached a crash by solving for this unknown here. And now we can kind of work our way backwards to figure out what the component is that you want to link against in order to cause this crash. Okay. So we figured out that that needed to be 0, the argument here, which means that now we've solved for the code, even though we started off, right, we didn't know anything about this code, but what we've done by running it against this kind of undetermined code and reaching a crash is we have figured out, look, here's the component you can link it against. And it is a function, so it's sort of not trivial, although this is a very simple example. It's not trivial that you can just synthesize the right function that will make this blue code crash, but we've done that here, okay? And it happens to be the same function that we had worked as an example, right? So that's kind of the mechanism for how you can construct these things. And given some program, you can automatically discover even the functional inputs that will cause it to crash. So what if we were to do it with that richer specification here that you would hope validates that the blue code is crash free? Well, we go through the same steps. Okay, so I'm going to just kind of jump through this quickly, and we get to this point where you say, okay, can you think of something that is an integer and not equal to 0 such that 5 over x crashes? And you can't. Okay, so you feed this off to an SMT solver and it says, no, there's no solution, which means that this code is safe, right? There's no crash here. So if we think about what that whole sub-expression in the original program produces, well, it produces some integer. We don't know what it is. And then the square function squares it. Okay, but that's a safe thing to do as well. There's no possibility of a crash there. And you've just symbolically run the program and you figured out that, okay, the only possible result is you get some integer back, but what doesn't happen is any crash that blames the blue part. So by symbolically running it, you have proved that the program is safe, okay? Here's, maybe for the sake of time, I'll sort of skip over this, but the high level idea here is here, I've gone back to that relaxed specification, but I've programmed defensively. Okay, so there's always this kind of trade-off between, do you put more information in the specification or do you program in a more defensive style? So here I've got the relaxed specification, but my program is going to check whether the input is 0 and do something safe in that case. Otherwise, it's going to do it. And symbolic execution works well in this setting where it sort of jumps through. We get to this point where it's, you think of an integer, but if you take the true branch, then you have to, everything is fine because there's nothing going on there and you get 1 back. If you take the false branch, then you have this constraint that, okay, because you take the false branch, x has to not be equal to 0, and you're thinking of 5 over x. Can you think of something that satisfies these constraints that crashes? And of course you can't, so this is also safe. Okay. All right. And these kind of steps that I've gone through, we can formalize this as a semantics for this symbolic language where you've got these unknowns and you've got some formula that represents the things that constrain these unknown values as you go. And I think the details here aren't really important. They're pretty simple, actually, but it's just as you compute, you sort of accumulate more knowledge about what the unconstrained or unknown thing here has to be. And then you can pass these things off to an SMT solver to solve for them. And the only kind of interesting thing you have to do is when you deal with calling unknown functions with some value from the program that you're trying to verify. And there's sort of two things that can happen. Either you get back some unknown value, or you interact with the unknown value. And the only way that you can interact with the unknown value is you apply it, in the case that it's a function, you apply it to something, you maybe get something back and interact with that. Okay. All right, so that's kind of the mechanism for automatically either discovering crashes or verifying that there aren't any. And if you sort of pay close attention to those details, one of the things that could happen is that the symbolic semantics runs forever. Okay, it didn't happen in the particular example that we stepped through, but you could certainly, for example, if the function you're trying to verify is a recursive function, then you can do this, back and forth between the symbolic context here and the program that you're trying to verify, and it'll just go on forever. Okay. So you got to have some way of dealing with that if you want to have a fully automated verification technique. And this part I'm going to just kind of gloss over. There's a big area in programming language research that works on how to soundly over approximate the behavior of programs. And the point here is I just composed this techniques from this world with the symbolic execution semantics that I showed you. And what you get is an over approximation of that symbolic semantics that I showed you. And let me skip ahead to the sort of relevant slide here. You use these techniques and it sort of tames the whole space of what your program might do. And it does it in a sound way, so that if you think about, each of those slides I showed you, think about those as kind of one state of the computation. And, the computation may proceed over, an infinitely long trace here. But what abstract interpretation does at a high level is it kind of collapses all of that stuff into like a finite directed graph, like I'm showing here, where each of the states of this is really representing some set of computational states that you can be in. And so you can just, you've now kind of solved the decidability problem where you can abstractly interpret the program, you get some finite representation of all the possible behavior that it can happen. And then you can start looking at it to do sort of a form of model checking on it. So you might say that, oh, look, it looks like if this state here is a contract violation, and so now it seems like it's possible to reach it. Now, what you know is that it may be possible to reach it. So this could be a kind of false alarm because of the approximation that the abstract interpretation is doing. It may be that, it says you could have a contract violation here, but in fact, there's no actual input to the program that can cause this to happen. So you only know that it may happen. But thanks to the soundness of the abstract interpretation, if there is no contract violation, if you look at all of the states here and none of them are contract crashes, well, then you know for sure, you're guaranteed that there's no possible contract violation when you run the program. So if there's no blame in the abstract semantics of your program, then there's no blame no matter what you run it against. Okay, no matter what you link it against and run. And if you have no blame in the program, then there's no need to monitor these things at runtime. So this is just sort of justifying an optimization that you can do, which is if you run your program against these contracts, you can say, well, I've statically verified them, and I can just go ahead and erase them, right? I've proven that they satisfy the contracts. And you have this other benefit that maybe there are some contracts that might fail at runtime and others that can't. but you can selectively optimize them and say, well, this one can't fail, I can get rid of that, but this one that I couldn't verify for whatever reason, maybe there's a real bug in the program, maybe my verification engine's not smart enough to prove it, you can leave that in and continue to monitor it at runtime. Okay. So this is kind of an example instance of this recipe that I showed you, where the runtime enforcement mechanism here is contracts. We're using symbolic execution, where the kind of novel technical thing there was dealing with functions as they flow across module boundaries. And then I skipped over this technique I use for abstract interpretation. So let me, I was overly ambitious for what I would cover here. And I've only got 5 minutes, but let me show you something that I think is kind of a cool, another cool instance of this recipe that I showed you, and I'll just give it to you sort of at a high level, which is, okay, if you think about sort of what we've accomplished now, you can take untyped programs, you can write down contracts, you can gradually verify them. You have some of the benefits of types because you can write down type-like contracts and statically verify them. But of course, it's even richer than that because the contracts can do things that like refinement types can do. You can have very expressive user-defined properties in your contracts, and you can verify them. But you're still talking about partial correctness, right? You're not talking about total correctness because you're not saying anything about termination, okay? So wouldn't it be nice to sort of scale up to, like, if you're going to scale up to theorem proving languages, you've got to deal with totality and termination. So how are you going to do it? Well, let's see, let's try to apply the recipe here. So you need a runtime enforcement mechanism for termination, and then some, symbolic execution and abstract interpretation. So, okay, the things we just need a check for termination that happens at runtime. Well, that's not going to work out very well for us, right? I mean, this is not just equivalent to the halting problem. This is literally the halting problem. And so we did this work that appeared at PLDI last year, where we did precisely this. Okay, so I mean, we didn't solve the halting problem, but we figured out a runtime mechanism that checks a property that is obviously not termination, but it's a over approximation of termination. So it's a property that we can check that implies that the program will terminate. Okay, and this was based on this fairly famous Popple paper, I think from 2001. That was about a static principle for proving your programs terminate, called the size change principle. And the idea of that paper in a nutshell, okay, is you take your program and you think about the call graph of the program. Like, so I've got these edges between calls to the Ackermann function that appear statically in this program, and you annotate them with some information about how the arguments change in size. And then you don't need to know the details here, but you take that, you take those annotations and you form a graph out of it, and you check this graph for some properties. And if it has this, what's called the size change property, then it tells you that, that there's no infinite cycle through the graph that isn't decreasing at least one of the arguments. And so it proves that it's a property that proves that the program terminates. But you're doing this statically over the static call graph. So we looked at that paper and said, there's a property here that is being, there's sort of two levels of approximation. One is the property, and the second is the call graph, okay? So let's take the property and check that at runtime, okay? And forget about the static call graph. Let's think about the real call graph that's happening as the program runs. And what we'll do is we'll check that, at each point that you make a call, we'll check that you're maintaining the size change property so far. And the moment that you see a violation of it, you stop the program and you say, no, 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 you violated the principle. So at that point, when we stop the program, either the program is definitely going to run forever, or the property got violated, but eventually it will terminate anyway, okay? So that's sort of the unfortunate case, and that's what, that's why it is an over approximation of deciding termination. But if you have a program that at all times has the size change principle, it's guaranteed to eventually terminate, okay? So, so now we have this kind of runtime mechanism, not for checking termination, but checking this property that implies termination. And we can have dynamic crashes that say you've violated the property. And now, I've sort of reduced this liveness property, verifying this liveness property down to a safety property, which is, can you reach a state where the size change termination principle doesn't hold anymore and a crash is signaled? So then you just kind of run it through the same machinery that I showed before, and you can recover a static verification technique from it, while also having these nice gradual properties of, if you can't verify something, you can just leave a check-in and run it and things like that. So by designing a different runtime enforcement mechanism, the whole, kind of recipe here still works out. It's actually kind of competitive with existing termination checkers for functional languages, and lets you run things dynamically, okay, which all these other static approaches, they have nothing to say about, either they prove your program terminates or they don't, whereas we can have these dynamic checks. Okay, so yeah, I'll end it there. Thank you, everyone. I'm happy to, I know that we're basically at time here, but if anyone wants to stick around for a few questions, I'm happy to answer questions.
Yeah, it's cool. We can keep going for a little
Okay,
while.
great.
Hello.
Hey, Jonathan.
Jonathan Aldrich here, Carnegie Mellon. Great talk. I really enjoyed it. Question about the last bit.
Sure.
Does the developer have to write the key invariant to get termination, the fact that M and N decrease in that order?
So the design that we have, it's really about what are the orderings on your base types that you want. And so the tool that we built, we basically make some default choices. And so as long as you want to use the defaults, you don't have to write any annotations. If you want to consider a different ordering, then you can just annotate things to say, no, I want to consider this other ordering. So but
I see. So like integers decreasing and bounded by 0 would be a natural default, but if you want them to be increasing and bounded by some other number, then
that's right.
You could say that.
That's right. Yeah.
Cool. Thanks.
Yeah.
So I have another question. Someone mentioned early in the chat about the gradual guarantee property.
Mm-hmm.
Is that something that fits in with your approach?
So the property being that if you, I always get this backwards, that if you have something that verifies and you remove annotations, it no, it's the
if it's at any stage of verification and you remove annotations, then you won't get any errors that you didn't get with more annotations. The idea is that the intuition is to go the other way, right? That
right.
If you add an annotation and it's correct, you won't get any more errors than you did before.
Right. So
the way it's formalized is kind of opposite.
Right. When you're talking about a gradually typed program, if you have something that is gradually well typed and you erase an annotation, that doesn't introduce any runtime errors. Is that right?
Yeah.
There are two components. It's both static and dynamic errors.
Right. Okay. So I haven't, I don't have proofs of any of these things, but it may be that it follows from some of the way that our soundness theorems are stated, because you can talk about, refinement, like you have a program that is more or less precise. So it may follow from that, but I mean, the honest answer is I don't know, and I'd have to look at it more to see. But I think that it is likely the case, but I'd have to.
Yeah, it
check.
sounds like it would, since you do more or less precise. I think, I mean,
Right.
I'm not an expert in it, but what I've seen, it's basically they provide this ordering of less and more precise, and then you prove it with respect to that. And I think if you have that, it would probably follow.
Yeah, I think that that's right.
So something that's probably going to show up is similar to the gradual refinement types work that we had, where you need a notion of precision that's not the syntactic precision that's traditionally used, but it has to kind of capture the semantic implication, the strengths of the specification as part of the precision.
Right. Yeah, and that we don't have. That's actually something I have a student that's sort of working on now, which is a more kind of semantic characterization of the contract correctness stuff here. And I think it phrased that way, then yeah, it should. Right, but I mean, you're just saying that you would need that in order to prove it, but I think that it's it's maybe true, but that we would have to do a lot more work to actually prove it.
Okay.
Yeah, thanks. Anything else?
And maybe just a quick question: Have you thought of have you looked at dependent types as part of general full dependent types in the contracts in your approach? How does that fit well? How does it work?
Well, we can have, I mean, the work that we've done has dependent contracts where, right, you can make statements in the return type of the function or the contract of the function that depends on the value that you give it as the argument. So that form of dependency works out fine.
But the more general,
but not the, I mean, the more general one we haven't considered. No.
Okay. Thanks.
Mm-hmm.
Great. So if does anyone else have any other questions for David? All right. Well, I guess we'll end it here. Thank you again so much, David, for such an amazing
pleasure.
talk.
Yeah.
I hope everyone stays safe, and thank you for coming to the colloquium.
Bye-bye.
Thank you very much.
Thanks, David, and thanks, Harley, for organizing.
Yeah, thanks for coming, Jonathan. It's good to see you.
You too.